Madam, 20 seconds.
Start, ma'am.
So good morning, dear students. Once again, welcome you all for the chemistry webinar. And today it's the time for the molecular orbital theory. And I would like to hand over the session to Mrs. Madhavi, PGT Chemistry from TSMS Pudur. And dear children, in our previous sessions, Madam has taught you the topics in chemical bonding. See, we have discussed the ionic bond, covalent bond, hybridization. And today it's the molecular orbital theory. So welcome Madhavi ma'am.
Thank you, ma'am. Thank you.
Thank you, ma'am. Thank you.
Good morning, everyone. A warm welcome to sixth session on chemical bonding and molecular structure. So, children, let us have a quick review. What are the topics that we have covered in previous session? Let us see. Types of overlapping and nature of covalent bonds. So, children, we know that atomic orbitals like s orbital, p orbital, d orbital, they overlap and they form different types of covalent bonds. Okay, so here in types of overlapping and nature of covalent bonds, we have discussed about sigma bond and pi bond. So what is a sigma bond? When s orbital, or s orbital, pz orbital, or pz orbital and pz orbital, when they overlap along the internuclear axis. What is internuclear axis? Z axis is considered as a internuclear axis. When they overlap along the internuclear axis head-on manner, say they form sigma bond. Okay, so which atomic orbitals they form sigma bond? S orbital, or s orbital, pz orbital, or pz orbital, pz orbital. When they overlap, they give sigma bond. How they overlap? They overlap head-on overlap. Okay, so that bond is called as a sigma bond. Now coming to the pi bond. So when px or py, they are perpendicular to the internuclear axis. What is the internuclear axis, children? Z axis is the internuclear axis. So px or py, they are perpendicular to the internuclear axis. Okay. So when they overlap in sideways manner, they give pi bond. Okay. So this is about the sigma bond and pi bond that we have discussed. Next, strength of sigma and pi bond. We know that the strength of the bond, it depends upon extent of overlapping. So sigma bond, in case of sigma bond, the extent of overlapping is more. That's why sigma bond is more strong when compared with the pi bond. Okay, these things we have discussed in the previous session, children. Next, hybridization. What is hybridization? Simply atomic orbital overlapping couldn't describe the geometry of a molecule like polyatomic molecules. For example, methane, next ammonia, water molecule, like that. If you consider polyatomic molecules, simply atomic orbitals. What are atomic orbitals? S orbital, p orbital, d orbital. So they simply overlapping, and that couldn't explain the geometry and orientation of the bonds. Okay, so that's why new concept, that is hybridization, has been introduced. So what is hybridization? The intermixing of atomic orbitals which are having nearly similar energy. Very important, children. 8-mark question. So what is hybridization? Intermixing of atomic orbitals which are having a nearly similar energy and gives new hybrid orbitals. Okay, so new hybrid orbitals are having the same energy and same shape, and they can able to overlap more efficiently than atomic orbitals. Okay, so in a hybridization, what we have seen, silent features of a hybridization we have discussed, and important conditions of a hybridization also we have discussed. Now this hybridization is many types. So depending upon the overlapping of or intermixing of orbitals, atomic orbitals, SPD orbitals overlapping, this hybridization is of many types. SP hybridization, SP2 hybridization, SP3, and D, SP2, SP3, D2, SP3D, like that many types of hybridizations we have. So in the previous session, we have discussed SP hybridization. What is SP hybridization? When one s orbital and one p orbital, they intermix together and they give two sp hybrid orbitals. The formed sp hybrid orbitals are having a similar energy and similar shape. Next example, in sp hybridization we have seen, children, BeCl2, beryllium chloride, is an example for sp hybridization. What is the shape of beryllium chloride? Linear shape, and the angle is 180 degrees. Next, in sp2 hybridization, what is sp2 hybridization? When one s orbital and two p orbitals, when they overlap and they give intermix together and give three sp2 hybrid orbitals. These three sp2 hybrid orbitals are having similar energy and similar shape. Okay, so example for sp2 hybridization, boron trichloride, BCl3, we have seen, children. What is the shape of boron trichloride? Trigonal planar shape, and the angle is 120 degrees, right? Next, after that, sp3 hybridization, we have discussed. What is sp3 hybridization? When one s orbital and three p orbitals, when they overlap and they give four sp3 hybrid orbitals. In that case, we have seen three important examples. Methane molecule. So in methane molecule, the structure is tetrahedral structure, and the angle is 109.5 degrees. Okay, children. So what are the other two examples for sp3 hybridization? Ammonia molecule. So ammonia molecule, nitrogen. Nitrogen is the central atom. That nitrogen undergoes sp3 hybridization. So on nitrogen, so one lone pair of electrons are present. Actually, for sp3 hybridization, it should get a tetrahedral shape, but because of the presence of lone pair of electrons, very very important, children, lone pair of electrons on nitrogen, it gets a pyramidal shape. Because of lone pair bond pair repulsion, it gets a pyramidal shape, and the angle decreases. So how much the angle in ammonia? Bond angle is 107 degrees. Actually, it should consist of 109.5 degrees, but because of the presence of lone pair and bond pair repulsion, it acquires a pyramidal shape, and the bond angle is 107 degrees, right? And one more example we have seen in sp3 hybridization. What is that? Water molecule. In water molecule, oxygen is the central atom. So oxygen undergoes sp3 hybridization. So on oxygen, two lone pair of electrons are present. So because of the presence of two lone pair of electrons, it acquires bend shape, and the angle decreases further, that is 104.5 degrees. Okay, actually it should get a tetrahedral shape, and the angle should it should consist 109.5 degrees, but because of the presence of two lone pair of electrons, it acquires bend shape, and the bond angle is 104.5 degrees. So these are the things that we have discussed in the last session, children. So now let us see what are the topics today we are going to cover. So hybridization. So other example, already we have seen SP, SP2 and SP3 hybridization. So in this class, we will discuss some more examples in SP3, SP2 and SP hybridization. Very important, children. Same thing you are going to learn in organic chemistry also. So in organic chemistry chapter, last chapter is there. So in that also, you're going to learn these hybridization. So listen carefully, learn perfectly. Okay, so in that, other examples of sp3, sp2 and sp hybridization. So ethane molecule, ethene molecule and ethyne molecule hybridization we are going to discuss. And after that, hybridization of elements involving d orbital. Till now we have discussed hybridization involving in s orbital and p orbital, but today we are going to discuss about the hybridization of elements involving d orbitals also, that is sp3d and sp3d2 hybridization. In sp3d, pcl5 formation. In sp3d2, sf6 formation we are going to learn. Okay, next one, molecular orbital theory. So next last one and very important from this, you are going to we can expect 8-mark question, very important children, molecular orbital theory. So in that silent features of molecular orbital theory and conditions for the combination of atomic orbitals. So these things we are going to cover today. So now let us start the session with hybridization. Some more examples of sp3, sp2 and sp hybridization. First, let us see sp3 hybridization in C2H6 molecule. So what is C2H6 children? Ethane. Two carbons are there and it is having all single bonds. So that's why it is ethane, C2H6. Okay. So in ethane molecule, if you see children, there are two central atoms, two carbons acts like a central atoms. So you know that in hybridization only central atom undergoes hybridization. Central atom, that two valence shell orbitals that are present in a valence shell only involved in the hybridization, right children? So carbon, each carbon undergoes sp3 hybridization and forms how many sp3 hybrid orbital children? So 4 sp3 hybrid orbital, because one s orbital and 3 p orbital. Total how many atomic orbitals are undergoing hybridization? 4 atomic orbitals are undergoing hybridization. That's why they form 4 sp3 hybrid orbitals. All these sp3, 4 sp3 hybrid orbitals are having the same energy and the same shape, right? Okay, so now see, after that, one of the 4 sp3 hybrid orbital of carbon atom overlap axially with the similar orbitals of other atom to form sp3 sigma bond. What is the children? So each carbon is undergone sp3 hybridization and it has formed 4 sp3 hybrid orbitals. Now after that, what happens? sp3 hybrid orbital of each carbon, one sp3 hybrid orbital of each carbon overlap with the sp3 hybrid orbital of another carbon and form sigma bond, that is called as sp3 sigma bond or cc sigma bond. Okay, and then now what is left? Three each carbon is having 3 more sp3 hybrid orbitals, because one sp3 hybrid orbital, it has formed sigma bond with another sp3 hybrid orbital of carbon. Now each carbon is having 3 more sp3 hybrid orbitals. So these 3 sp3 hybrid orbital on each carbon, they form sigma bond with s orbital of hydrogen atom. Okay, so you can see here children, each carbon in ethane, how many carbons are there? 2 carbons are there, and these are the central atoms. They undergo sp3 hybridization and they can form 4 sp3 hybrid orbitals. These blue color are nothing but 4 sp3 hybrid orbitals. So one sp3 hybrid orbital of a carbon and one sp3 hybrid orbital of this carbon, they overlap and they form sigma bond. Now each carbon is having 3 more sp3 hybrid orbitals. These 3 sp3 hybrid orbitals, they overlap with the s orbital of hydrogen, because s orbital of hydrogen is having one unpaired electron. So this sp3 hybrid orbital of carbon is also having one unpaired electron. You can see in this figure clearly. So sp3 hybrid orbitals, so each carbon forms 4 sp3 hybrid orbitals, and this sp3 hybrid orbital of this carbon and sp3 hybrid orbital of this carbon, they overlap and pairing will takes place and it forms sigma bond. Now each carbon is having 3 sp3 hybrid orbitals. These 3 sp3 hybrid orbitals, they overlap with the s orbital of hydrogen, and again here also pairing will takes place and they form CH sigma bonds. So CC sigma bond, see children here, CC sigma bond, because sp3 overlap gives a sigma bond. So this is CC sigma bond, and sp3 and s overlapping, sp3 hybrid orbital of carbon and s orbital of hydrogen overlap, it gives another sigma bond, that is CH sigma bond. So total how many sigma bonds are there? 1 CC sigma bond and 6 CH sigma bonds. 1, 2, 3, 4, 5, 6. So 1 CC sigma bond and 6 CH sigma bonds present in ethane molecule. Is it clear, children? Each carbon undergoes sp3 hybridization. So form 4 sp3 hybrid orbital. sp3 hybrid orbital of each carbon overlap and form one cc sigma bond, and each carbon is having 3 more sp3 hybrid orbitals. These 3 sp3 hybrid orbitals overlap with the s orbital of hydrogen and they form ch sigma bond, and the bond angle is, if it is sp3 hybridization, bond angle is, that is 109.5 degrees. Okay, so this is about sp3 hybridization in ethane molecule. Next, coming to sp2 hybridization in ethene molecule, C2H4 ethene molecule. So sp3 hybridization in ethane molecule and sp2 hybridization in ethene molecule. Here in between carbon and carbon there will be double bond. Okay, so now let us see, children, in ethene molecule also having 2 carbon atoms. Each carbon undergoes sp2 hybridization and form how many sp2 hybrid orbitals? 3 sp2 hybrid orbital, because 1 s orbital and 2 p orbital, total 3. That's why it will form 3 sp2 hybrid orbitals. Okay, so now listen, children, each carbon is having one unhybridized p orbital because only 1 s orbital and 2 p orbitals involved. That's why each carbon is having one unhybridized p orbital, because only carbon consists of 2p. In 2p, 3 p orbitals are there, 2px, 2py, 2pz, but only 2p orbitals involved in the hybridization. So 1 p orbital is unhybridized in each carbon, right, children? So you have to remember that. Next, after that, one sp2 hybrid orbital of each carbon, it will overlap with the sp2 hybrid orbital of another carbon and form cc sigma bond. Okay, so now you can see in this figure, children. So each carbon is undergoing sp2 hybridization, and this one, this orange colored one, these 3 are sp2 hybrid orbitals of carbon. So now each carbon is having one unhybridized p orbital. P orbital is having dumbbell shape. That's why this green colored one shows that unhybridized p orbital. So this is the condition of one carbon, but in C2H4 we have 2 carbons. So this carbon, each carbon undergoes sp2 hybridization, so and form 3 sp2 hybrid orbitals. sp2 hybrid orbital of this carbon and sp2 hybrid orbital of this carbon, they overlap and they form sigma bond, and then now each carbon is having 2 more sp2 hybrid orbitals. Is it not, children? So because already one sp2 hybrid orbital is involved in the cc sigma bond formation, now each carbon is having 2 more sp2 hybrid orbitals. So these 2 sp2 hybrid orbital on each carbon, they overlap with the s orbital of hydrogen and they form ch sigma bond. This is ch sigma bond. Is it clear, children? Again I am repeating. So in ethene molecule C2H4, each carbon undergoes sp2 hybridization and form 3 sp2 hybrid orbitals. So one sp2 hybrid orbital of each carbon, they overlap and they form cc sigma bond, and it is having 2 more sp2 hybrid orbitals. These sp2 hybrid orbitals, they overlap with the s orbital of hydrogen and they form sigma bonds. So now listen, here each carbon is having one unhybridized p orbital. This is one unhybridized p orbital. This is one unhybridized p orbital. These unhybridized p orbitals on each carbon, they are perpendicular to the plane. They are perpendicular to the plane. So that's why they overlap sideways manner. So they overlap sideways manner. See this, children, here how they overlap. They overlapped perpendicular to the planes in a sideways manner. So once they overlap in a sideways manner, they form pi bond. Okay, so here you can see in this figure clearly, here one sigma bond. So how CC sigma bond, how it is formed? SP2 hybrid orbital of carbon and SP2 hybrid orbital of carbon, when they overlap, they give CC sigma bond. So, and these are CH sigma bonds. Okay, so next these are unhybridized p orbitals. These are perpendicular to the plane, so that's why they overlap in a sideways manner and they give pi bond. Now in ethene molecule, one CC sigma bond and one CC pi bond and 4 CH sigma bonds are present. Is that clear, children? This is about ethene. Very simple. Okay, one CC sigma bond and one CC pi bond and 4 CH sigma bonds are present in ethene. Now coming to another one, that is SP hybridization. So see children, in SP hybridization, so example we will consider C2H2. C2H2 is ethene molecule, ethyne molecule. So in this, in between carbon and carbon, there will be a triple bond, C2H2. There will be triple bond. Let us see how this triple bond is formed between two carbons. Okay. So in this also, the central atom is carbon. Carbon undergoes sp hybridization. So one s orbital and one p orbital, when they combine together and they give how many sp hybrid orbitals? Two sp hybrid orbitals, because two atomic orbitals overlap and give two sp hybrid orbitals. So once these two sp hybrid orbitals, out of these, one sp hybrid orbital of one carbon atom overlap axially with the sp hybrid orbital of the other carbon atom to form CC sigma bond. Let us see here. You can see children here. So each carbon undergoes sp hybridization and form two sp hybrid orbitals. These are the two sp hybrid orbitals, children. So each sp hybrid orbital of each carbon, it overlap with the sp hybrid orbital of another carbon and it forms CC sigma bond. Now each carbon is having one more sp hybrid orbital. So that sp hybrid orbital of each carbon overlap with the s orbital of hydrogen. This is the s orbital of hydrogen, children. So it forms CH sigma bond. This is CC sigma bond and this is CH sigma bond. Okay, is that clear? Now what else it is having? The other hybrid orbitals of each carbon atom overlap axially with the half-filled s orbital of hydrogen atom, form sigma bond, that is CH sigma bond, right? Now see children, here only one p orbital of a carbon is involved in the hybridization. Now each carbon is having how many p orbitals which are not involved in the hybridization? 2, because p orbitals to px, to py, to pz. So out of 3, only one p orbital is involved in the hybridization. Now each carbon is having so 2 unhybridized p orbitals. So now you can see in this figure. So these are the 2 unhybridized p orbitals which are perpendicular to the plane. So these are the 2 unhybridized p orbital. In this figure, we have shown only sp hybridized orbitals, whereas in this case we have shown only the unhybridized p orbitals. So this is one unhybridized p orbital, that is 2py, and this is one more unhybridized p orbital, that is 2px. Each carbon is having 2 unhybridized p orbitals, so they are perpendicular to the plane. Now how they overlap? They overlap in a sideways manner. If they overlap in a sideways manner, which type of bond will form? Pi bond. Okay, is it clear, children? Again I'm repeating. Carbon, it is having 3 p orbital, 2px, 2py, 2pz, but only one p orbital is involved in the hybridization. Each carbon is having 2 unhybridized p orbitals, to px and to py. They are perpendicular to the plane. So how they overlap? They overlap in a sideways manner. If a sideways manner overlap, So which type of bond it gives? Pi bond. You can see in this figure, children, CC sp hybrid orbital of this carbon and sp hybrid orbital of this carbon, they overlapped and they give a cc sigma bond, and each carbon is having one more sp hybrid orbital, so they overlap with the s orbital of a hydrogen and form ch sigma bond. Now if you see, each carbon is having two unhybridized p orbital, this blue colored one unhybridized p orbital, so dumbbell shape. See children, so this blue colored one is unhybridized p orbital and this yellow colored one dumbbell shape, so this is also another unhybridized p orbital. So these two p orbitals are, that is p to px and to py, they are perpendicular to the plane, they overlap in a sideways manner and they give pi bond. See children, this blue colored one and blue colored one, this is 2px and 2px of this carbon, they overlapped in a sideways manner and given pi bond, and this yellow colored one 2py and 2py, they are perpendicular to the plane, so that's why they overlap in a sideways manner and forms pi bond. So it means that in between carbon and carbon there is a one sigma bond and two pi bonds, and two CH bonds are present in ethyne. So this is the hybridization in case of ethyne, children. So lot of practice is required. So very easy. Go through this. Next one is hybridization of elements involving d orbitals. So in that we'll see formation of PCl5. So hybridization of elements involving d orbitals, sp3 hybridization. So one s orbital, three p orbitals and one d orbital. Once they overlap and they intermix together and they form how many sp3 hybrid orbitals? So because here five atomic orbitals are intermixing, so that's why we'll get 5 sp3 hybrid orbitals. Okay, so example we'll consider, children, PCl5. In PCl5, phosphorus is the central atom. So what is the atomic number of phosphorus? 15. Okay, so electronic configuration 1s2, 2s2, 2p6, 3s2, 3p3. So we'll consider only outer shell configuration, is it not? 3s2, 3p3, outer shell configuration 3s2, 3p3. So in 3s, 2 electrons are present, and in 3p, 3 electrons are present in ground state. So in excited state, 1 electron from 3s, it will enter into the 3d. Okay, so it means in excited state, 3s is having 1 electron and 3p is having 3 electrons, and 3d is having 1 electron. Now 1 s orbital, 3 p orbitals and 1 d orbital. So they overlap, they intermix together and they form the 5 sp3 hybrid orbital. You can see in this figure, children, clearly. So 5 sp3 hybrid orbitals, 1, 2, 3, 4, 5. So total 5 sp3 hybrid orbital. Phosphorus forms, phosphorus undergoes sp3 hybridization and forms how many sp3 hybrid orbitals? 5 sp3 hybrid orbitals. So this purple colored one shows the hybrid orbitals. Each sp3 hybrid orbital is having similar shape and similar energy, and they overlap very efficiently. They form covalent bond very efficiently. That's why they are undergoing hybridization, right, children? Okay, so now see here, phosphorus is a central atom in PCl5. So it forms sp3 hybridization. It undergoes sp3 hybridization and forms how many sp3 hybrid orbitals? 5 sp3 hybrid orbitals. Now each sp3 hybrid orbital is having one unpaired electron. Now see children, in chlorine electron in PCl5, it is having 5 chlorines. Each chlorine atomic number is very important, 17. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p5. If you see, each chlorine is having one p orbital which is having one unpaired electron, p orbital which is having one unpaired electron. P orbital, what is the shape of p orbital? dumbbell shape, and chlorine is having how many p orbitals which are having unpaired electron? Only one p orbital which is having unpaired electron. So now each chlorine which is having one unpaired electron in its p orbital, it will overlap with the sp3d hybrid orbitals of phosphorus, and it will form pcl sigma bonds. So how many pcl sigma bonds total? Total 5 will get the PCl sigma bonds, children. So, and the shape is trigonal bipyramidal structure. Trigonal, this is the structure, trigonal bipyramidal structure. So, children, here, if you see the structure, the two types of bonds are present. So, one type is axial bonds, PCl. These two are called as axial bonds, and these are called as equatorial bonds. So PCl, these three are called as equatorial bonds, and these are called as axial bonds. So children, here when compared with equatorial bonds, axial bonds are little bit longer. Why they are little bit longer? Because in order to avoid bond pair repulsion, because each bond pair, this axial bond, if you consider each bond pair, it acquires a repulsion from 3 more bond pairs from the equatorial bonds, is it not? So that's why to avoid the repulsion, these axial bonds, they are little bit longer when compared with the equatorial bonds, right children? So this type of structure is called as trigonal bipyramidal structure. When phosphorus PCl5 phosphorus pentachloride, phosphorus undergoes which type of hybridization? sp3d hybridization. One s orbital, 3 p orbitals, and 1 d orbital. Once they overlap or intermix together, and they form how many sp3d hybrid orbitals? 5 sp3d hybrid orbitals. Okay, and the shape is trigonal bipyramidal structure, and two types of bonds are present. So axial bond and equatorial bonds, two axial bonds and three equatorial bonds. These axial bonds are little bit longer when compared with the equatorial bonds, because they are experiencing more repulsion from bond pairs. Okay, so and the bond angle, see children, in equatorial bonds the bond angle is 120 degrees, because they are present in a triangle, equatorial triangle. So that's why the bond angle is 120 degrees, whereas this axial bonds, the bond angle is 90 degrees, because they are perpendicular to the plane. So that's why the bond angle is 90 degrees, right children? So in PCl5, what is the structure? Trigonal bipyramidal structure, and bond angle 120 degrees in equatorial bonds, and 90 degrees in axial bonds. So this is about the formation of PCl5 in sp3d hybridization. Next, coming to so this is the structure. See children, this is trigonal bipyramidal structure. These are the sp3d hybrid orbitals, 5 sp3d hybrid orbitals, and p orbitals of each chlorine, they overlap and they form PCl sigma bonds. How many PCl sigma bonds? 5 PCl sigma bonds. Shape is trigonal bipyramidal structure. In equatorial bonds, the bond angle is 120 degrees, and for axial bonds, bond angle is 90 degrees. So this is about the structure of PCl5. Now coming to sp3d hybridization. In sp3d hybridization, children, one s orbital, 3 p orbitals, and 2 d orbitals, they overlap, they undergo hybridization, and they form how many sp3d2 hybrid orbitals? 6 sp3d2 hybrid orbitals. Why 6 sp3d2 hybrid orbital? Because 1 is 1 plus 3 plus 2, total 6. 6 sp3d2 hybrid orbitals will get. Now see the example for sp3d2 hybridization. Sulfur hexafluoride, SF6, is an example for sp3d2 hybridization. In this case, what is the central atom? Sulfur is the central atom. What is the atomic number of sulfur? 16. So what is the electronic configuration of sulfur? 1s2, 2s2, 2p6, 3s2, 3p4. Now, what is the outer shell electronic configuration, children? 3s2, 3p4. So, this is the outer shell electronic configuration of sulfur. So, we'll consider only for bond formation, only our concentration is on valential electrons and valential orbitals. So we have here 3s and 3p. So in 3s 2 electrons and 3p 4 electrons, right? So ground state 3s is having 2 electrons and 3p is having how many electrons? 4 electrons. But in 3d no electrons are present. 3d is empty, is it not? So now in excited state we'll send one electron from s orbital into d orbital and one electron from p orbital into d orbital, right? Now see here in excited state, S3s is having one electron and 3p is having 3 electrons and 3d is having 2 electrons. Now what happens? One s orbital, 3p orbitals and 2d orbitals, once they overlap and they form sp3d2 hybridization. So they form how many sp3d2 hybrid orbitals? 6 sp3d2 hybrid orbitals. You can see in this figure, children. See how many sp3d2 hybrid orbitals are there? 1, 2, 3, 4, 5, 6. So sulfur sp3d2 hybridization and it formed how many sp3d2 hybrid orbitals? 6 sp3d2 hybrid orbital. Now coming to the fluorine. So in SF6 total 6 fluorines are there. You know the atomic number of fluorine, children? So 9. Electronic configuration is 1s2, 2s2, 2p, 5. So in fluorine, each fluorine is having one p orbital which is having one unpaired electron. So p orbital is having dumbbell shape. So p orbital of a fluorine which is having unpaired electron, it will overlap with the sp3d2 hybrid orbital of sulfur and it will form sp sigma bond, that is sp3d2 and p sigma bond. Okay, so like that how many sigma bonds will get? Sf sigma bonds total 6 sigma bonds will form, because in SF6 how many fluorines are there? 6 fluorines. Each fluorine is having one p orbital in which unpaired electron is present. It will overlap with the sp3d2 hybrid orbital of sulfur and it will form sigma bond, and the structure will be octahedral structure. So this is called octahedral structure, children. So these 6 fluorines, they form sigma bond with sulfur. So this is the octahedral structure and the angle is 90 degrees, bond angle in sp3d2 hybridization. So how much? It is 90 degrees. Okay, so again I am repeating. In SF6, sulfur undergoes sp3d2 hybridization and forms 6 sp3d2 hybrid orbitals. Each sp3d2 hybrid orbital is having one unpaired electron. Now it is in SF6, 6 fluorines are there. Each fluorine is having one p orbital in which one unpaired electron is present. One p orbital is having one unpaired electron. So that p orbital which will overlap with the sp3d2 hybrid orbital of sulfur and it will form sigma bonds, like that total sigma bonds for 6 sigma bonds will get. Okay, so then that structure is called as octahedral structure and the bond is bond angle is 90 degrees. So this is about sp3d2 hybridization in SF6, children. So this is about hybridization. Now coming to some other examples for elements hybridization in which d orbital is also involved. Square planar d sp2 hybridization. So if a central atom undergoes d sp2 hybridization, then it acquires a square planar structure. What is d sp2 hybridization? When one d orbital, s orbital and two p orbitals, once they undergo hybridization, they form d sp2 hybrid orbitals. How many d sp2 hybrid orbitals will get? Two total 4 d sp2 hybrid orbitals will get, big children, because 1 plus 1 2, 2 plus 2 4, 4 d sp2 hybrid orbitals will get, and the structure will be square planar. And so example for such d sp2 hybridization is NiCN4 2 minus and PtCl4 2 minus. Next one is sp3 dehybridization. So when one s orbital, 3 p orbital and 1 d orbital overlap and give sp3 dehybridization. So in that case, structure is trigonal bipyramidal structure. And example already we have seen PCl5 and PF5 are the examples. Next one is sp3 d2 hybridization. It means one s orbital, 3 p orbitals and 2 d orbitals. Once they overlap and they give sp3 d2 hybridization. So square pyramidal structure. Actually, it should consist of octahedral structure. sp3 d2 hybridization means octahedral structure. But because of the presence of lone pair electrons, see in BR5, it is having one lone pair of electrons. So because of that, it acquires a square pyramidal structure. Next one is sp3 d2 hybridization or d2 sp3 hybridization. So it means one s orbital, 3 p orbital and 2 d orbitals. Once they overlap, they give sp3 d2 hybridization. So structure is octahedral structure. Example for this type of a hybridization, SF6 already we have seen children, and CrF6 3 minus and CONH3 6 3 plus. So these are the examples, and other examples for hybridization involved in d orbital. Okay children, so you just practice all these things. Next, coming to another last topic and a very very important one, that is molecular orbital theory. So it is developed by F. Hund and Mulliken. So now let us see the silent features of this theory. So electrons in molecules are present in various molecular orbitals, as the electrons of atoms are present in the various atomic orbitals. We know that children, in atoms, so the electrons are present in atomic orbitals. What are atomic orbitals? S orbital, p orbital, d orbital and f orbital, is it not? So in atoms, these electrons are present in atomic orbitals. Now first tell me, what is orbital? Orbital is nothing but orbit and orbital. What is orbit? Orbit is nothing but the circular path around the nucleus in which these electrons are revolving. What is orbital? Orbital is nothing but probability density of a electron around the nucleus. Probability of finding an electron around the nucleus is called as orbital. So s orbital, p orbital, d and f we have, depending upon the shapes. Okay, so now in atoms, the electrons are present in atomic orbitals, that we know that. So up to 20 electronic configuration you have learned, that is hydrogen 1s1, helium 1s2 and lithium 1s2 and 2s1. Like that, we know that the electrons are in atomic orbitals. Okay, but in molecules, where these electrons are present in molecular orbitals. Very simple children. First point, like electrons present in atomic orbitals in atom, in molecules, electrons will be present in molecular orbitals. Okay, so if it is atom, atomic orbital; if it is molecule, molecular orbital. That's all very simple. First one. Next, coming to the second one, the atomic orbitals of comparable energies and proper symmetry combine to form molecular orbitals. So how these molecular orbitals are formed? These atomic orbitals, they combine and they form. So but how, which type of atomic orbitals they should combine? Which are having comparable energies and proper symmetry, then only they can able to form molecular orbitals. Okay, so an electron in an atom orbital is influenced by one nucleus, because suppose if you consider a hydrogen, one electron is present, that is influenced by nucleus of that hydrogen, is it not? So in atoms, electrons are influenced by the one nucleus, because in atom only one nucleus is present. But whereas in case of electrons in molecules, how they influenced by more than one nucleus, because molecule is formed by the combination of two or more atoms, is it not? For example, water molecule, if we consider, it is formed due to the combination of one oxygen atom and two hydrogen, H2O. So two hydrogen atoms and one oxygen. So how many nucleus are present? Three nucleus are present. So the electrons in that molecule, they are influenced by three nucleus. So like that, electrons in molecular orbitals, they influence by two or more nuclei depending upon the number of atoms in the molecule. So, while a molecular orbital is a polycentric, whereas atomic orbital is monocentric, because in atom only one center is present, whereas in case of a molecule, so there are many centers, because if it is formed by two atoms, then three centers will be two atoms, then two centers will be present. If it is formed due to three atoms, then three centers will be present. Four atoms, if it is formed, then four centers will be present. That's why molecular orbital is polycentric, whereas atomic orbital is monocentric. So next one, the number of molecular orbitals formed is equal to the number of combining atomic orbitals. So suppose two atomic orbitals, if they combine and they give how many molecular orbitals? Two molecular orbitals. Okay, so the number of molecular orbitals formed is equal to the number of combining atomic orbitals. When two atomic orbitals combine, they give two molecular orbitals. So one is known as bonding molecular orbital, while the other is called as anti-bonding molecular orbital. Is it clear, children? When two atomic orbitals combines, they give two molecular orbitals. So one molecular orbital is called as bonding molecular orbital, and another one is called as anti-bonding molecular orbital. So bonding molecular orbital is having less energy and a greater stability than the corresponding anti-bonding molecular orbital. Again, I am repeating, when two atomic orbitals combines, they give two molecular orbital, and one molecular orbital is called as bonding molecular orbital, and another molecular orbital is called as anti-bonding molecular orbital. Okay, so bonding molecular orbital is having a less energy and more stability. Okay, and anti-bonding molecular orbital is having more energy and less stability. You can see here, children. Just as the electron probability distribution around the nucleus in an atom is given by atomic orbital. Just now only we have discussed. Atomic orbital means the probability of finding the electron around the nucleus is called as um, atomic orbital. Like that only, the probability distribution around a group of nuclei in a molecule is called as molecular orbital. Same. Okay, what is that? The probability of finding the electron around the nucleus in an atom is called as atomic orbital. Whereas in case of a molecule, there are many nucleus are present. That's why the probability of distribution around a group of nuclei in a molecule is given by molecular orbital. The molecular orbitals like atomic orbitals are filled in accordance with the aufbau principle, obeying the Pauli's exclusion principle and Hund's rule. Okay, we know the children, we know that electronic configuration, how we have written. So the electrons filled in atomic orbital depending upon three principles. One is aufbau principle, Pauli's exclusion principle, and Hund's rules. So like that only in the molecular orbitals also, the electrons will fill according to these three principles. What are the three principles? Aufbau principle, Pauli's exclusion principle, and Hund's rule. So in atomic orbitals, how the electrons are filled, how the electrons are filled according to these three principles. Aufbau principle, Pauli's exclusion principle, and Hund's rule. Like that only, molecular orbitals like atomic orbitals are filled in accordance with the Aufbau principle, obeying the Pauli's exclusion principle and Hund's rule. Right? Okay. Now, see here, children, two atomic orbitals are combining. So psi A and psi B. Psi A and psi B represents the wave functions of two atomic orbitals. So how they are combining? So this is the linear combination. Linear combination means plus or minus. So it may be plus or it may be minus. So when the wave functions of these atomic orbitals, once they undergo a linear combination, they give two types of molecular orbitals. So this is the molecular orbital. So two types of molecular orbital. If it is plus, then it is called sigma, that is bonding molecular orbital. If it is minus, then it is called sigma star, that is anti-bonding molecular orbital. Sigma and sigma star are molecular orbitals. See children, psi A and psi B are the wave functions when the wave functions of these atomic orbitals, once the addition takes place, then it gives bonding molecular orbital. If a subtraction takes place between the two atomic orbitals, then it gives a anti-bonding molecular orbital, that is sigma star, sigma and sigma star. So molecular orbital sigma is called bonding molecular orbital, and sigma star is called as anti-bonding molecular orbital. Just now only we have seen bonding molecular orbitals are having less energy and more stability, and anti-bonding molecular orbitals are having high energy and less stability. You can see children here. So two atomic orbitals, once they undergone addition, if it is addition in between two atomic orbital, then it gives bonding molecular orbital. So, and if it is a subtraction, then it gives anti-bonding molecular orbital. Anti-bonding molecular orbital is represented with a star, sigma and sigma star. Sigma is the bonding molecular orbital with low energy and a high stability, and anti-bonding molecular orbital is having more energy and less stability. Sigma and sigma star. Sigma is molecular orbital, sigma star is anti-bonding molecular orbital. Okay, so condition for combination of atomic orbital. So this thing we'll see in the next session, children. So now let us see what are the topics that we have covered in this session. Hybridization. So what is a hybridization? So it is an intermixing of atomic orbitals and gives new orbitals called as hybrid orbitals, which are having similar energy and similar shape. In that, many types of hybridization we have discussed: SP, SP2 and SP3. So in that, many examples also we have discussed in previous session. So in this session also we have covered some more examples. So C2H6 ethane molecule, SP3 hybridization, and C2H4 SP2 hybridization, C2H6 ethane molecule, SP3 hybridization, and C2H4 ethene molecule, SP2 hybridization, C2H2 ethyne, so SP hybridization. In this, in C2H6, all are single bonds, all are sigma bonds, whereas in case of C2H4, one pi bond is formed, and whereas in case of C2H2, two pi bonds will form. Right, children? So we have discussed today. Next, after that, we have seen SP3 dehybridization. In that, we have considered the example of PCl5. In PCl5 central atom phosphorus, it has undergone SP3 dehybridization, formed 5 SP3D hybrid orbitals, and shape is trigonal bipyramidal structure, and it is having equatorial bonds and axial bonds. The bond angle between equatorial bonds is 120 degrees and axial bonds is 90 degrees. So all these things we have discussed. And after that, we have seen SP3D2 hybridization. So example, we have considered SF6 is an example. Central atom SP3D hybridization. It formed 6 SP3D2 hybrid orbitals, and structure is octahedral structure, and the angle is bond angle is 90 degrees. So after that, we have seen molecular orbital theory. In that, the silent features we have covered today, but conditions for the combination of atomic orbital in the next class we will cover, children. So what are the silent features of molecular orbital theory? When atomic orbitals they combine, they give molecular orbitals. When two atomic orbitals combine, they give two molecular orbitals. One is bonding molecular orbital, another one is anti-bonding molecular orbital. Bonding orbital sigma, and anti-bonding molecular orbital sigma star. Sigma is having low energy, that is bonding molecular orbital is having low energy and more stability. Whereas in case of anti-bonding molecular orbital, that is sigma star, it is having more energy and less stability. So what else we have discussed in silent features of molecular orbital theory? How the electrons are filled in these molecular orbitals according to three principles, that is Pauli's exclusive principle, aufbau principle, and Hund's rule. So what is Pauli's exclusive principle, children? No two electrons in an atom can have all four quantum numbers same. And what is aufbau principle? Electrons lower energy orbital will fill first than higher energy orbital. Next, what is Hund's rule? Um, that we have discussed in last session. Okay, so conditions for the combination of atomic orbitals that we will discuss in next session, children. Thank you so much. I hope you have understood the session. Go through this. Thank you, ma'am. Thank you for this opportunity.
Thank you, Madhvi ma'am. So it was a very clear session today children had. So dear children, today madam has explained you regarding the chemical bonding. That is a hybridization topic, and also she has very clearly explained you about the molecular orbital theory. And children, here I want to tell you about the important principles, that is the aufbau principle and Hund's rule, right? So whenever the electrons enter into the orbitals, they will enter into the lower energy levels first, and then only they will enter into the higher energy levels. So whenever degenerate orbitals are available, see what are degenerate orbitals? Orbitals having nearly same energy are called as degenerate orbitals. See, whenever degenerate orbitals are available, pairing of electrons takes place unless they are completely half filled. Okay, so that is called as Hund's rule. So please learn all these rules before going to the molecular orbital theory. So please watch our YouTube channel, and then see children, this is the 6th day of chemical bonding. This is a very big chapter. You are having many topics in this. See, ionic bonding, covalent bond. Then madam has explained you about the hybridization and what are the different types of hybridization and all. So please learn all this and write down the notes. So ma'am, in our next session, we are going to learn about the linear combination of atomic orbitals, isn't it, ma'am?
Yes,
And
ma'am.
you are going to explain the MOED diagrams also for different molecules. Okay.
Formation of oxygen and nitrogen molecule, different molecules in molecular orbital theory.
Yes, ma'am. Yes, ma'am.
Very important.
Okay. Okay. So thank you, ma'am. Thank you very much for your sincere efforts for making these webinar sessions a very successful one. See, because I know the efforts what you are like putting all. Thank you very much. Thank you, Madhvi ma'am. And I
Thank you,
thank each and everyone for giving us this opportunity.
Thank you.